Hi and welcome to Functional Just in video 6. So in the last one we talked a lot about functors, but I didn't get a chance to talk about the Functor laws because the video was 20 minutes long and I really want to keep these videos quite short. So this time we're going to start with the Functor laws, and then I'm going to show you how I've packaged the Functor into its own module, and then we're going to look into using it in the expression evaluator. So the expression evaluator is going to be working with the either numeric type to handle both the concept of being a numeric and also having error handling. And to really handle errors properly in a nice principled way, we're going to need to introduce monads, and then we're going to introduce applicatives. So it's going to be super quick. I'm just going to show how they're used and just briefly how they're implemented. And then once we've done that, we'll demonstrate a different error. We've already implemented missing symbols in the expression evaluator. What we'll do is implement division by 0. So that's it. So let's get into the code. In the last video we were implementing Functor, and I showed you how to implement a given instance for Functors. So using this we can use Functors on eithers with any error type, and we're using type lambdas. There's a type lambda right there to make that work. And the last video ran on a bit, 20 minutes long, and I really wanted to keep these videos to around 15 minutes ideally, so I cut it short. But one thing I wanted to talk about, I didn't get a chance to talk about, was Functor laws. So the idea is that we're making an abstraction based on a mathematical abstraction called Functor, and to do that we need to implement the map function, which we've done. And the map function basically behaves the same as the one in the Scala standard library. So when you map a list, it doesn't matter whether you use our Functor or if you use the standard library, it's exactly the same. But the reason we've encoded it as a Functor is to communicate to the compiler and to other programmers that we're using this abstraction and it's going to behave in a way that according to the Functor laws. So here's the Haskell documentation on Functor, and you can see that there's two Functor laws that we've got to adhere to be a valid Functor. So let's just give an example of how they work. So also since last time I moved the Functor into a module, so Functor now has its own package, and we have, let's just have a quick look at what we've got. So we've got the companion object, and all that has is this function that lets us bring the Functor into existence if we need it. And then we've got the trait, which represents the Functor's or the type class's interface to the world. So basically we just implement the fmap function. And the reason I call it fmap is just so that we don't interfere with Scala's standard map. And then this is the instance for lists, which is quite straightforward. And then we've got the instance for either, which is a little bit more complicated because either has two type parameters. So we want to be able to derive instances for eithers with any error type. So we made another type parameter for that, and then that gets passed into this type lambda. So that's a bit more tricky than the list, but it's not that complicated, and that gives us the capability to do what we want. So now what's interesting here is to import that package. I've got to use two things. First of all, when you import things in Scala 3, you don't get any givens by default. So this wildcard argument will bring in everything except the givens, which means implicit instances, and then you can import the givens separately, right? So this is sort of a wildcard too. This brings in all of the implicit instances of Functor, and what we could do is we could just bring either, or we could just bring in list. But we're going to use both, so we'll bring that. So the reason these two things are separated out is to give you more control, and so that if you don't know where an implicit came from, you can go up and look at the imports, and hopefully that will give you more idea and save you some time. So let's talk about the Functor laws. As we can see, there's two. Functors must preserve identity morphisms. Functors must preserve composition of morphisms. So those two things sound very clever and mathematical, but they're really just expressing simple ideas. So the first one is, let's say we have a list. What the identity law is saying is if we map the list, well, let's just, sorry, I'm going to print the result of this. So the list itself is equal to, if we take the list and we map the identity function. So I'm just going to write it like this to make it very clear what's going on. So we take the list and we compare that to mapping the list with the identity function. So in other words, we don't change the list, we just create a new list with the same contents. So if I run that, and you can see that the result is true. So that means that for lists, the identity function holds, and we can also do the same thing for either. So let's make an either with the string error type. And we can do the same thing here. So we could have a right value, say like this, and then we're going to map over it with the identity function and make sure that it does not change. So this would be equal to E1 map identity. So this is just an abbreviated way to write this, of course. Alright, so you can see the output is true. So in these two cases, the identity law holds. So the next thing we want to look at is composition of morphisms. So what that means is if we have two functions, we want to be able to apply the functions in separate maps, or we can apply them in a single map composed together, and it should give us the same result. So let's say we have this function that just increments a number, and we have another function that decrements a number, and what we're going to say is that the list L1, and we fmap that with I should actually be using my map, shouldn't I? There we go. It doesn't actually change anything, but I should be using the one that we implemented. So same here, we want to take the either and we want to map it with the f function, and then we want to map it again with the g function. Now what composition says is if I was to fmap this with the composition of f and g, so in other words that means we take a and we apply f to a, and then we take the result of that and apply g to it, that is the morphism that we want to remain the same. And that's true. And we can do the same thing with list. So if you ever wonder whether a data type is a valid functor or not, one thing you can do is plug in the values to some of these laws and make sure that it behaves according to the laws. If it does, then it's a valid functor. Alright, so next thing I'm going to look at is, let's go back to our expression evaluator. So the expression evaluator is something that takes expressions. So an expression looks like this. It's an abstract syntax tree of expressions, and then we have an eval function that takes each expression and decides how to evaluate it, passes it on. So what we end up with is in the end we end up evaluating using these functions, which are on numeric. And so at the very top here, what we've got is a given instance for quite a complex type. So first of all, we're looking for a numeric instance of type A, right? So A is the type of number that our expression evaluator will be working with, and then we create the given instance of this type, which is a numeric that has type either eval error A, right? So instead of just working with numbers like we did last time, we've extended it to be an error type. So to make this work so that our code compiles, which as you've seen it does, then we can just add numeric eithers together like that. We can go in here and try and use the Functor to make it work for us, because these are ethers. You can see the type definition just there. So what we need to do is get into the value of a. So we could use the fmap for that. And I'm just going to show you the type there. So what is the type we get back here? It's any. Or it shouldn't be any, but I have to do a bit more work here first. So we fmap the a, and that will give us another a. Just let me rename these things here. So this is fa, this is fb, and then we're going to fmap fa. Then this gives us an A. Right, so now we should be looking at an A. So the next thing we want to do is, because we have a numeric instance here, we want to use the add function to add it to the B. But we can't get to the B, so we need to do fb fmap, and that gives us the B. And then we can use the plus function to add them together. Now this is not the regular plus function, this is the plus function in our numeric type. Right, so we could, another way we could write this is, because we know we have an implicit instance of a's numeric, we could summon the numeric like this, summon numeric a, and then we can call the add function and pass the a and the b. But because we've defined the simple operators and the extension methods, then we can write it like that. Okay, so now we look at the type of E. Oh, it's still any. It shouldn't be any. I think that's just a mistake in the ID. So here we're going to get an error. So what we found was an either val error. Right. So in other words, it's nested, but we didn't want it to be nested. So obviously we need something more than Functor, and the something that we need is monad. So this is not going to be a monad video, but I already made a monad earlier, so I'm just going to make the text bigger, because in the last video the text was a little bit small on some of the parts of the video. Alright, so here's a monad. So this is implemented exactly like the Functor last time. Exactly the same style. So we have a companion function with an apply that lets us bring a monad into existence whenever we want it, and then we define it as a trait. So this defines various methods. So all monads have a pure function, which takes a pure value and turns it into an effect of that type. And then we have some extension methods. So we've got Flatmap, which is named to disambiguate it from the built-in Flatmap. You can see that I've also inherited from Applicative for monad, which brings in the app function and also the map function. So I'm also not going to talk about Applicative much in this video, apart from how to use it, but probably in a later video we'll go into both of these things in more detail, right? So how the heck is a monad going to help us? Well, monad has Flatmap, right? So if you look at the function signature here of Flatmap, it takes a function that takes a pure value and creates an effectful value. But just like Functor, it still maps a FA to an FB. So it has the right type signature to fix our problem here. So the type inferencing is not working, so that doesn't help. It doesn't help us too much. What I wanted to show you was why we need to use Flatmap. But we can go ahead and make this into a Flatmap. After I import it. So this needs to be monad, not applicative. Sorry, my bad. So I've imported the monad, and now we can call Flatmap. And now we can return this, and that should be the right type. So the reason that's the right type, and it wasn't the right type before, is because Flatmap includes a flattening operation. So it took the result of this second map, which would have been a nested either, and then it flattened it. So what we've done there is taken advantage of the fact that there's a monad instance in scope, and we use that to flat map the first value, map the second value, and then we can run basic numeric operations on them. It's actually nicer to do this with applicative than monad, so there's nothing wrong with doing it with a monad, but it's actually a bit more powerful than what we need. So applicative, we switch to the applicative package. Doesn't actually have Flatmap, but it does have a much easier way to do this. So what I'm going to do is just take a quick look at the applicative package and show you what's going on there. So applicative is somewhere in between Functor and Monad in terms of power, and you can see that I've actually extended Functor to make the applicative. Applicative adds the pure function, which we also have in Monad, but it also has this app function, which is another mapping. So far we've seen map, we've seen flat map, and app is a very similar operation that maps from a effective type A to an effective type B. And app itself takes this weird signature. So what it takes is a function that's itself in an effect. So for example, if you had an either and you wanted to map it with app, you'd need your function to be inside an either as well. You apply it. So it's a tricky signature. But the nice thing about app is it gives us the power to apply multiple effects to a pure function. So we can go through each of the effects and get the values from them and apply them to a pure function. So to that end, I've created the map2 function. Now map2 is a lot easier to understand than app, and you can see that it's derived from the map function and from app. So this is a derived method, so you don't have to write this for your own applicative instances. You only have to implement app. Now if you want to do it the other way around, you can also implement app in terms of map2. So it doesn't matter which way around you do it. So some instances it might be more efficient to write map2, others it might be more efficient to write app. But the advantage of map2 is it's much easier to understand. It looks more like normal Scala code, and you can go ahead and write map3, map4 for increasing numbers of parameters, and you could even do a macro to write map_n, and then you can take any number of parameters and apply them to some function that has a certain arity. So what we want to do is we've already brought the applicative into scope. We're going to use the map2 function here, and you'll see that this works a lot nicer for the use case. So we just take the FA, and then we're going to call map2 on it, and the first parameter is the second parameter of the function, so FB. And then the third parameter would just be a function that takes two parameters. So in our case, we're going to take the A and the B, and we're going to just add them. And remember, we've got a numeric in scope, so even though we're not dealing with regular numbers, we have a numeric in scope, so that's literally all we need to do. So you can see that I've already been busy and implemented all of the rest of the functions this way. So I can go ahead and run the expression evaluator now, and you can see it doing its stuff. So we've got two example expressions that are showing their output down here. So the first one just printed 45, which means it succeeded. And then the second one demonstrated what happens when things go wrong. So we used the A symbol, and so when we looked at it in the symbol table, it would have thrown an exception. Sorry, it didn't throw an exception, it created a left value, so we've principally handled the error, and then we just print it out and we've got symbol not found. So it's a much nicer way to handle errors than just throw an exception, for example. This is just some test operations to test all the new stuff I added. So another thing we're going to do is show how to add more error handling. So we're going to handle division by 0. So this is the division function, and then we're taking a raw value 10 and we're dividing it by 0. So in the until we do some special code, this is just going to throw a real exception and break our program. So you can see we got a division by 0 when we did the divide. So to fix this, what we're going to do is go to the numeric type and add the concept of a number being 0. So we want to be able to add a function is 0 that the user can define to tell us whether a number is 0 or not. And then we've got to implement it for our instances. So is 0 this is just going to be if a equals 0, and then for our funny string number type we would just say is 0. We're just going to say it's 0 if the length of the string is 0. Now we've got some error here. Now remember that this special thing is an instance of numeric 2, so this also needs a concept of 0. And it's going to take a type eval result a and return a boolean. And the way to implement this is to just match it like because it's an either. So what we want to do is we're going to look inside the either and get the value out. And then we're going to check if it's 0. So we want to call 0 on the instance of numeric a. We want to call is 0 on that. So basically look inside the option, see if you find a 0 in there, and if you do, then true, the number is 0. Pretty much anything else we just want to return it. Alright, so now our numeric type has the concept of a number being 0. So let's add a new error in the eval error for division by 0. Now what we can do is go to the divide function, and we can actually implement the error handling here. So we don't have to add this for the other instances because they don't have a way of handling errors. This one does. So what we're going to do is first of all check if it's 0. So we're interested in the b parameter, which is the divisor. So if b is 0, if is 0 b, then what we're going to return is an error division by 0. And I didn't import that, so we just have to type it and fully qualify it like that. And then otherwise we return the actual division. So we got an error there. My bad, just a syntax error. Alright, so now we've added error handling for division by 0 for any numeric type. And that did not work. I just got to fix this test. It should actually be checking for eval error division by 0. Alright, so now we run it. And there you go, and now you see that all of these asserts are passing. So that's the end of this video. Just to recap, what we looked at was error handling with Functors, Applicatives, and Monads, and then we implemented division by zero by extending the numeric class so that the numeric class understood the concept of being zero. So I hope this was helpful. There's a few things we're going to look at in future videos. One of them is to look at monads in more depth, applicatives in more depth, and others will be to continue to look at Scala 3 features. So if you enjoyed the video, please like it, subscribe to it, and maybe watch some of the other videos, and otherwise, see you next time. Thank you.